Okay, let's look at Taylor series in numerical analysis. We have seen the formula for the nth order Taylor series, and this gives the approximation of a function near a point x. So we take f of x plus h. H is typically small, so the x plus h will be close to x. X is called the expansion point. And we write f of x plus h as a sum of f of x and derivatives of x at the derivatives of f at the point x. This is the first derivative of f at the point x, second derivative of f at the point x, and so on. If I take an nth order polynomial, that means it's nth order in h. This is called the nth order Taylor polynomial. Now, this polynomial is only approximate. It's not an exact representation of the function, and we can bound the error. The error in the formula will be less than the Taylor error bound, which is given by this. There should be absolute values here. Let's go fix that quickly. This should be maximum, and this should be absolute value. So let's just get that out of the way. All right, so in other words, to find the error bound, I have my h, which I know if I'm trying to approximate the function at x plus h. And n is going to be the order of my polynomial, so I know n. And then I'll have to compute, or theoretically find, a bound, an upper bound, on the absolute value of the n plus first derivative of f. So sometimes you don't have to be exact about this. You just have to make sure you choose a number here that's bigger than the n plus first derivative. So if you have a function that you know how to take derivatives of, this is a fairly straightforward process. Well, let's see how this works in the case of a function that we do know how to take the derivatives of. Our exercise is to complete the following code that computes and plots, got to put the s there, the seventh order Taylor series approximation in Taylor error bound for f of x equals cosine x, the expansion point x equals 0 on the interval minus 3 to 3 with increment 0.01. Increment means that's the distance between successive values of h. So in other words, we're going to compute this formula for lots and lots of h's in such a way that we get all the values of x plus h between minus 3 and 3 with increment 0.01. Okay, you could use linspace or you could use arange to do that. We'll see how we can do that in a moment. All right, let's begin. First of all, we need to import some packages. Or the packages we need to import are, whenever you're plotting in Jupyter, you always need 3 statements. This one here, which is specific to Jupyter, this percent is called a magic statement. In most Python, you don't need these. Right, that's a Jupyter statement. Second one is import NumPy. And I prefer to import NumPy this way because it makes your code look a lot more like MATLAB. And then the plotting routines come from matplotlib pyplot. Okay. Now, in this particular code, we also need the factorial. So I'm going to import factorial from the math package. Right. So that's all the packages we need. And let's go on to the next section. So we'll put a comment there. All right, now we need to initialize. Whenever you have arrays, it's better to set them first so that you know where to put your data. All right, now in the Taylor series formula, you need to find derivatives. Our function is cosine. So I encourage you to write down on a piece of paper, what are the derivatives of cosine when x equals 0? Now, if you remember your calculus, the derivative of the cosine function is sine. Minus sine, rather. Derivative of minus sine is minus cosine. Derivative of minus cosine is sine. And derivative of sine is cosine. So, in fact, the derivatives go in a period of 4. Cosine minus cosine, sine. It just repeats in 4 like that. And we have to start with the zeroth derivative, which is just the function itself, We know cosine of 0 is 1, and then sine is 0, so we're going to get 1, 0, minus 1, 0, and that pattern is going to repeat. So we can do this, and we'll call this deriv, because these are the derivatives. That's going to be equal to, and let's make it an array, because we have NumPy. And here we have 1, 0, minus 1, 0, because I'm evaluating at 0. Whoops, minus 1. And then this pattern is going to repeat. So I'm going to copy and paste. Now I want 7th order. So that's 8 terms because the first term is 0th order. So 0, 1, 2, 3, 4, 5, 6, 7. 7th order. All right. Now I want the 7th order. Order is the same as degree. And so I want 7th degree. Now I could just say the degree equals 7. But it's better not to repeat your variables. If I have this array of derivatives, I can compute the degree from there. So I'll call this n is my degree or order. And that's going to be equal to the length of deriv. Now the length of deriv is 8 because I also included the 0th derivative. So I need to take the length of deriv minus 1. And that's going to give me my order. Right now, we need the maximum absolute value of the n plus first derivative, because that's what appears in this formula. Now, fortunately, the derivatives of cosine are either cosines or sines, and cosine and sine is always less than 1 in absolute value. So no matter where you are, cosine and sine is always less than 1. So in this case, I can use the maximum n plus 1th derivative as 1. So other cases, what may not be so simple, I gave myself an easy example to do. So max abs n plus 1 deriv is equal to 1. All right, so that's something I have to calculate theoretically. So let's see. So I need an array with the h values. Now, my interval is from minus 3 to 3, and my x is 0. So that means h will go from minus 3 to 3. Now be careful here. If x were not 0, then h would not be from minus 3 to 3. For instance, if x were 1, then the minimum h would be minus 4, because to get down to minus 3, I have to take 1 minus 4. And the maximum h would be 2, because if I start with 1, my expansion point, then I go up 2 to get to the other limit. So be careful. In this case, I'm lucky because I have x equals 0. So my expansion point is 0. I already have that here. So my h is going to be, I can use a range. And I'm starting at minus 3. I'm going up to 3, but I have to go a little past 3. Otherwise, 3 won't be included. So I'll do that. And my step is 0.01 because that's what was set up here. The increment was specified. I already have the expansion point, and then I need to create an array to contain the Taylor series. Now I'm going to get a Taylor series value for each value of h. So I can say Taylor, and I might as well start with zeros. And the number of entries has to be the same as the number of entries in h. All right, so I'm ready to go. I have all my initialization, all the arrays that I need. All I need to do is compute this for each value of h. All right, so I'm going to compute n plus 1 terms, and I can do this for all h's at once in a loop from 0 to n. So that's what I'm going to do. My loop is going to go from, I'll call my loop variable n, and I'm going up from 0 to n, so it's just range of n plus 1. If you remember, range of n plus 1 goes from 0, does not include n plus 1, it goes up to n. I need a colon for a for statement. And here I need to get my Taylor series. So Taylor. Now I need to keep adding terms to Taylor. So it's going to be Taylor. See, I'm starting out with 0, and then I need to add terms. And that's going to be, my term is going to be h to the power n over factorial of n times the derivative of n. Right? So that's going to give me my h. And this will work for every h because these numbers will be applied to every entry in the vector h. Right? And that actually finishes my loop. I've done all the h's at once. Now, if you're going to be more conventional or use other language like C++, you would have to loop through the values of h. But here, if I'm going to code efficiently, I want to do all h's at once. This is the power of arrays in Python. All right, so this gives me my Taylor series. So I need to compare that to my actual function values. And so I'll call that actual. And that's going to be equal to, my actual function is cosine. And here's going to be cosine of h. And I really should say this should be cosine. Whoops, how did that happen? Don't know how that happened. All right, anyway. All right, now here I should put, instead of h, I should put cos of my expansion point plus h, because those are my actual values. All right, and then I want the error, the error between the actual and Taylor series. So this is going to be actual abs error. This is the actual error because in this case I know the correct value of the function. I've got that here. It's going to be equal to the absolute value of the Taylor minus actual. And then I can compute the theoretical error. Okay. The theoretical error will be, let's see, we're going to have to use this formula here. So it's going to be, let's call it theoretical, and I want the absolute error, so absolute error. That's going to be equal to the absolute value of, just follow this formula here. It's going to be h star star, and then this is n plus 1, because n is my degree, whoops, plus 1. And let's make sure, I think that's okay. And then divided by factorial n plus 1 times, and then I'm going to use, whoops, times the maximum value of n plus 1 derivative, which was called max abs n plus 1 derivative. So I have my absolute value around here. I actually should go back and correct this. You actually need an absolute value around this also, because if h is negative, you have to make sure that you have a positive value. So I'm going to put an absolute value here. All right, so I think we're good. Let's go back down here. So I got my Taylor. Now I don't put an absolute value here. I need the sign here. But here, when I'm computing the error, I do need the absolute value. And let's see if my parentheses match. My parentheses seem to match. Okay. So this is my theoretical error. Now again, I'm computing my actual x values are the expansion plus h. So I need to do that. So that's going to be, I'll say x actual. That's going to be equal to the expansion point plus h. Right? So I'm done with my calculation. Now what I want to plot are the x values versus the actual function Taylor series and the errors. Okay, so I want two plots, and I'm going to do plots using the object-oriented style plotting, which is not the style that I presented in the tutorial, but it's useful and it's easy to understand. All right, so let me just put this out and you can see how it works. This is, I'm going to have the fig and axes is equal to subplots and rows equals 1 and cols equals 2 and fig size equals 8. All right, all this is saying is that I'm using, this is just like using the subplot command that's going to have one row of plots with two plots side by side. And this is going to give me two sets of axes. Axis 0 is going to be the figure on the left, and axis 1 is going to be the figure on the right. So I want to attach to axis 0 the first plot. So that's going to be axis 0. And this is going to be, I want to plot my function. Now my actual x values are x actual, and my Taylor series is Taylor. And let's make this one red. It's okay. And I need to label this because I'm going to do a legend. So I want to plot both the Taylor series and the actual value. So I'm going to copy this and paste it. But in this case, I don't want Taylor. I want the actual, which is the actual function. Let's call this actual function because then just make that a little bit clearer. Actual function. And let's make this different. I'll do a b dot, and we'll have to call this actual function. All right. And let's go ahead and put a legend on this. I'm going to attach a legend. You can put the legend to different places. It turns out that this location variable allows you to put it in different places. This actually is located in the upper left. You can try different locations. Location 1, 2, 3, 4 will all work. And then I want to set a title. So all of these things, the plot and the legend and the title, are properties of these axes. They're attached to the axes. These are objects. This axis is an object, and I'm attaching different properties to that object. So that's why this is called object-oriented programming. Okay. This is the Taylor series for cosine. I think that's okay. All right. Now, so this is for the left, and now I want to do for the right. Okay. Now let's go ahead and I already have the figure axes. I'm going to copy this statement and modify it. Now in this case, I still want to plot. I want axes of 1. I still want to plot x actual, but instead of the Taylor, I want to plot the actual error. So the actual error is actual abs error. And let's see. I don't need to assign a color. We'll just let Python assign a color itself. And this label will be actual absolute error. And then I'm going to plot also the theoretical absolute error. So x actual is the same. And then here I'm going to want theoretical absolute error. Okay. And this is going to be theoretical. And here I'm going to put also a legend and a title. So I'll just copy these because that's convenient. I don't need these blank lines. I'll get rid of them. And here my legend is going to be on axis 1. So it's attached to axis 1. And then this is going to be the actual and theoretical errors. And let's see if this worked. I'm sure I'm going to have some problems, but that's what coding is all for. So I'll press Control Enter. It will take a little while. All right, so let's see what's wrong. Okay, it's good practice of reading error messages. Here it says invalid syntax. So that means I typed something wrong. And I guess it's not too hard to figure out what I typed wrong here. Form is not from. So let's go ahead with from. A little debugging practice here. Okay, that looks better. I'm going to save it. Run again. Let's see what we got this time. Another error. This one's in line 38. Doesn't look too difficult to find this one. I'm missing my equal sign. I guess my equal sign stuck. Now I should say that here, the line number 38, you can toggle your line numbers by, let me see if I can do this. I think if you go to View, if you look at View, and I think it will do toggle line numbers. That's very useful to have line numbers when you're debugging. Okay, so let's try again. Control Enter, and it's compiling, it's thinking. We got another problem. Again, we can figure out what this is. I changed actual to actual fun. So I didn't change it here, so in line 36, I've got to go ahead and do that. Let's see where that is, line 36. Actual fun. I hope you're having actual fun with this. Okay, so let's go ahead and do this. Run it again. And it's running. Let's see what we got now. All right, and we got something, and it looks pretty good. All right, now, here's this text output. I think you can remove that if here you put display at the end. And I think that will get rid of the text output. Let's see. Yeah, display gets rid of it. And there you have your whole code. All right, so nice, complete cookbook recipe for Taylor series code. Most of this is comment. The actual code is probably only like 20, 30 lines. Okay, hope you enjoyed the video.